By midsummer, the main emigrant road along the Platte is a moving line of wheels. Federal reports and later summaries estimate that wagon parties on the Oregon-California routes typically covered 15 to 20 miles per day, day after day, for up to 6 months. Freight companies hauling government supplies across similar country, by contrast, held their loaded trains to roughly 10 miles or less to preserve animals and gear over 600-mile hauls. The loads are similar. The road and weather are the same. The difference lies under the beds, in the way wood and iron share shock, or fight each other. Most wagons of the period use bolts and hot-set rivets through oversize holes. They roll with constant clatter, fifth wheel plates, hub bands, brake irons all working loose. A smaller number begin to leave certain rivets cold and slightly oversize, swelling them into the wood instead of shrinking out of it. On these planes, the math is simple. If the same team can move the same load an extra mile without new feed or new road, the quiet wagon wins. Dust hangs low over the river valley. Wheel tracks cut deep into hardpan. Iron tires click on buried cobble as a freight train eases away from the morning camp. The sound carries across flat grass, a rhythm of metal on stone, wood on wood, harness jingle, and underneath it all, the constant rattle of hardware working loose. Distance on the trail is decided by many things. Route choice matters. Weather and water matter. Animal strength matters most of all. But there is another factor, quieter and less discussed: the mechanical resistance and failures in the wagons themselves. Contemporary accounts focus on terrain and teamwork. They describe the challenge of river crossings, the search for good grass, the need to rest animals before they break down. What they mention less often is how the wagons themselves limit daily miles just as much as any grade or stream. The wagons moving west in the 1850s fall into two broad categories. Emigrant families travel in prairie schooners, relatively light vehicles with beds about 4 feet wide and 10 feet long, carrying a ton or more of household goods, tools, and provisions for the journey. These outfits, when well managed and not overloaded, can average 15 to 20 miles per day over the course of the season. Freight operations use heavier equipment. Government contractors and Army suppliers run trains of Conestoga-type wagons, some capable of hauling 3 to 6 tons. These trains, operated by firms like Russell, Majors, and Waddell, deliberately limit daily travel to protect stock and equipment. 10 miles in a day is good progress. 12 is exceptional. The reasoning is straightforward. A heavily loaded wagon puts more strain on animals and hardware. Push too hard and you destroy both. But the loads are not always that different. A well-packed emigrant wagon carries 2,000 to 2,500 pounds. A freight wagon might carry 3 to 4 tons, but it is also built heavier, with larger wheels and stronger running gear. The road is the same packed dirt, loose sand, or rocky hardpan. The weather and grass are identical, yet one outfit covers twice the distance of the other. The difference lies in the power budget. Draft animals, oxen or mules, can pull a certain amount on level ground, more with effort on a grade. Rolling resistance depends on the surface. Hard dirt or grass requires less pull than soft ground or sand. Stop-start losses in rough terrain waste energy that could have moved the load forward. With fixed animal power and fixed loads, only 3 levers remain to improve daily distance: route choice, driver habit, and the mechanical efficiency of the wagon itself. Most contemporary documents discuss the first two. Emigrants debate which ford to take or where to find the best grass. Freight managers argue about rest schedules and how hard to push teams. This narrative focuses on the third lever, the wagon, specifically on the joints where wood and iron come together and how those joints behave under thousands of miles of vibration and shock. National Park Service summaries of emigrant trail guidance describe 15 miles per day as the ordinary planning figure. They stress the risk of overdriving teams, which leads to broken-down animals and stranded parties. What the summaries do not emphasize is that mechanical failures, broken wheels, loose hardware, collapsed running gear, create the same risk. A wagon that spends half a day stopped for repairs is a wagon that does not make its miles. On a 2,000-mile journey, adding even 1 mile per day without changing the route, or the team removes nearly 2 weeks of exposure and feed. That is 2 weeks less risk of early snow in the mountains, 2 weeks less chance of running out of supplies, 2 weeks more margin against disease or accident, but only if the wagon will let it happen. A new wagon stands on blocks in a yard in Independence, Missouri. The paint is still sticky. Beneath the bed, the running gear shows fresh iron, straps, clips, and plates, punched or drilled and pinned into seasoned wood. To most customers, a wagon is a unit. It is either sound or unsound, well-built or poorly made. The buyer looks at the wood, checks the wheels, tests the tongue, and makes a judgment. The wagon is purchased as a single object. In practice, the wagon is a collection of joints. Each fastener, each bearing surface, each point where iron meets wood or wood meets wood has a specific job. Some joints carry vertical load, the weight of cargo pressing down through the bed to the running gear. Some handle twist, as the wagon flexes over uneven ground. Some resist side thrust when the vehicle turns. How these joints behave under load determines whether the wagon moves efficiently or fights itself with every rotation of the wheels. The front running gear is the most complex assembly. At its center is the fifth wheel, a rotating connection that allows the front axle to swing left and right for steering. The king bolt passes down through the front bolster, through circular iron plates called bolster plates or fifth wheel plates, through a wooden sandboard, and finally through the front axle itself. This single bolt holds the entire turning assembly together. Around the king bolt are additional components: circle irons that guide the rotation, sway bars that limit side-to-side rocking, and straps that tie the bolster to the hounds, the long wooden members that connect front and rear axles. Every one of these parts is fastened with bolts, rivets, or pins driven through drilled or punched holes. The design works. Tens of thousands of wagons built this way cross the continent, but the joints are not perfect. Each hole is drilled or punched slightly oversized to allow easy assembly. Iron shanks slip through wood with a little clearance to spare. The intent is speed. A smith or wheelwright can pin a joint quickly if the hole is generous. On the road, that clearance becomes a problem. When the wagon hits a bump or crosses a rut, the bed surges forward and then back. The iron hardware shifts in its holes. The king bolt taps against the edge of the bolster. Hub bands rock against their fasteners. Brake hangers knock against their pins. Each impact is small, but over thousands of miles, the cumulative effect is significant. The iron shank polishes the wood around it. Fibers crush and compress. The hole becomes larger. What started as a 1/4 inch of clearance becomes 1/2 inch, then more. A joint with clearance does not share load the way it should. Instead of the surfaces clamping together and transferring force through friction, all the load concentrates on the fastener shank. The joint behaves like a hammer striking an anvil, converting steady forward pull into impact, noise, and accelerated wear. This is the hidden cost of loose joints. The wagon still moves. The animals still pull. But more of their effort goes into fighting the wagon's internal movement instead of overcoming rolling resistance. The result is higher peak loads on the tongue, more fatigue on the team, and a slower average pace. Every audible clank in a moving wagon marks a place where power is being spent to hammer iron instead of move freight. A print volume sits open on a bench. The date is 1891, but the notes collected inside describe problems from earlier decades. One short entry stands out: a complaint about reach bolts working loose, nuts dropping off, and wagon stays splitting under road vibration. The reach is the long wooden member that connects the front and rear running gear. It must handle both tension and compression as the wagon flexes over uneven ground. Standard practice is to secure it with bolted iron stays, straps that wrap around the reach and bolt through the hounds or bolster. The blacksmith writing the note describes what happens in service. The yaw bolts and nuts hold for a while. Then, under constant vibration, the nuts begin to back off. Once they loosen, the strap shifts. The bolt shank begins to work in the wood, elongating the hole. Eventually, under a sudden shock, a deep rut, a buried rock, the reach splits. The writer is not blaming weak iron or bad roads. He is identifying a design problem. Joints that rely on threads and shrink fit alone, with no intentional clamp or preload, will shake themselves loose under long-distance wagon work. Other entries in the manual describe similar issues. Screws and bolts in carriage work are described as always working loose. Hub bands shift and require constant tightening. Brake hardware develops play, leading to sudden grabs and uneven wear on the shoes. The pattern is consistent across different builders in different regions. Wagons subjected to continuous vibration suffer predictable failures at fastened joints. The failures begin with small clearances. Over time, vibration turns those clearances into large gaps. Eventually, something breaks. Modern readers might assume the solution is simply to use larger bolts or stronger iron. But the blacksmiths writing these notes are not asking for heavier hardware. They are asking for better ways to fasten it, methods that prevent movement in the first place. The physics are straightforward. A fastener can hold a joint in two ways. It can resist shear, the force trying to slide the parts past each other, by having a strong shank that does not break. Or it can create clamp load, pressing the parts together so that friction between the surfaces carries most of the load. A loose joint relies entirely on shear strength. All the force concentrates on the fastener shank, which taps against the hole edges with each bump and surge. A tight joint where surfaces are clamped together distributes load across a much larger area. The fastener is still there, still contributing, but it is no longer doing all the work. The trade journals of the late 19th century document a slow shift in thinking. Early wagon work prioritizes speed and simplicity: punch a hole, drive a bolt, move on. Later practice, informed by years of field failures, begins to emphasize precision. Drill clean holes to specific sizes. Use fasteners that fit closely. Design joints to maintain clamp load over time. By the time these notes are published, the men under the wagons are no longer asking whether bolts loosen. They are asking how to build joints that cannot rattle themselves apart. A rivet glows orange in a forge. The smith pulls it with tongs, drops it through a plate and wooden member, and upsets the tail in quick hammer blows while the shank is still hot. The entire operation takes seconds. The rivet cools, the joint is complete. Hot riveting is standard practice in the late 19th century. It works flawlessly in all iron joints, bridges, boilers, railcars. The rivet is heated until it is soft enough to deform under the ihyo hammer. One end, already formed into a head, is backed against the work. The other end is upset into a button. As the rivet cools, it contracts, pulling the parts together. In metal-to-metal joints, this creates a permanent, tight connection. But in mixed wood and iron wagon work, the same method introduces long-term problems. The first issue is hole size. To insert a hot rivet quickly, before it cools too much to work, the hole must be oversize. A rivet that is 3/8 of an inch in diameter might require a 7/16 inch hole. That extra 1/16 of an inch is clearance, and it remains after the rivet cools. The second issue is what happens inside the joint as the rivet cools. Iron contracts as it loses heat. In an all-metal joint, this contraction creates clamp load. The rivet pulls the plates together. But in a wood and iron joint, the hot rivet also heats the surrounding wood. Fibers are compressed and sometimes lightly charred. As the wood cools and dries, those fibers relax and shrink away from the rivet shank. The result is a smooth tunnel, slightly larger than the rivet, with a loose fit. Over time, as the wagon cycles through wet and dry conditions, wood shrinks further in dry weather. The gap around the rivet increases. What began as a tight joint becomes a loose one. The third issue is how the joint behaves under vibration. Once clearance exists, the rivet shank can move in its hole. Every bump sends a small shock through the hardware. The rivet taps against the wood. The hole polishes and enlarges. The loose fit accelerates wear. Blacksmithing manuals of the period describe the process in detail. Standard Blacksmithing, Horseshoeing, and Wagon Making, published in 1907, emphasizes the need to heat rivets to the proper color, not too hot, or the iron becomes hot short and brittle, not too cool, or it will not upset properly. The manual assumes that speed is essential. Heat the rivet, place it, upset it, and move to the next joint before the iron cools below working temperature. The method is optimized for production. A skilled smith can drive dozens of rivets in an hour. But the technique embeds a risk. Every hot-driven rivet in a wood and iron joint is likely to develop clearance over time. This does not mean hot rivets fail immediately or catastrophically. Many wagons built with hot riveted joints serve for years, but they require constant maintenance, tightening, reclinching, replacement, and they never run as quietly or efficiently as they could. The same process that locks flanges on a boiler can quietly build rattle into a wagon joint before the first mile is traveled. A length of mild steel rod sits on a bench. It has been sheared to length and headed in a swage, all at room temperature. Unlike its red-hot cousin, this finished rivet cools in air and goes into the bin at ambient temperature. Conventional shop wisdom says, "Strike while the iron is hot." The phrase is literal. Most heavy shaping work requires heat to soften the metal. Cold iron is hard and brittle. Strike it with a hammer and it cracks or chips instead of deforming smoothly. But not all iron behaves the same way. High-carbon tool steel is hard and brittle, even at heat. It must be heated carefully and shaped within a narrow temperature range. Quench it wrong, and it shatters. Mild steel and wrought iron, by contrast, are ductile. They contain little carbon and have a soft, fibrous structure. They can be bent, headed, and upset at room temperature without cracking. Blacksmithing manuals distinguish between these materials carefully, warning smiths not to confuse tool steel with mild steel. The latter can be worked and welded at higher heat without becoming brittle, and it retains enough ductility when cold to be shaped by controlled hammering. This property, the ability to deform plastically at room temperature, makes mild steel suitable for a different kind of riveting. The process is straightforward. Drill a clean hole, fractionally smaller than the rivet shank. Insert the cold rivet, back the head firmly against one side of the joint. Drive controlled blows on the other end until the shank begins to swell, pressing outward against the walls of the hole. Continue upsetting until the tail forms a button and the shank has expanded to fill the hole completely. The result is a rivet in full contact with the surrounding material, wood and iron, along its entire length. There is no clearance, no room to rattle. The shank has plastically deformed into the exact shape of the hole, pressing outward with residual stress. This creates clamp load without relying on thermal shrinkage. The rivet head and tail bear against the outer surfaces of the joint, compressing them together. Friction between the clamped surfaces carries much of the load. The rivet shank is still there, still resisting shear, but it is no longer the only thing holding the joint together. The technique is not universally known in the mid-19th century, but it is not entirely new either. Carriage builders and machinery shops already use cold-driven rivets in certain applications, particularly where tight tolerances are required. The innovation, to the extent there is one, is recognizing that the same method can be applied to wagon joints, and that doing so eliminates the chronic loosening that plagues hot riveted wood and iron connections. There are trade-offs. Cold riveting is slower than hot riveting. The smith must drill the hole more precisely, control the upset more carefully, and apply more blows to achieve the final shape. But the joint, once made, requires far less maintenance. It does not loosen with vibration. It does not develop play as the wood cycles through wet and dry seasons. Instead of relying on a hot rivet to shrink tighter, frontier smiths could make a cold rivet grow until there was nowhere left for it, or the joint, to move. A wagon stands jacked up beside the road. The front axle has been swung aside, exposing the scored circle irons and slack riveted straps around the fifth wheel. The repair will take half a day. The train must wait. Not all rattle is equal. Noise at loose sideboards or a shifting load is annoying but costs little. Slack at the fifth wheel, brake hangers, and hub bands drains power and threatens catastrophic failure. The fifth wheel is the steering pivot. It must allow the front axle to turn while supporting the full weight of the bed and cargo. The king bolt passes through the front bolster, the bolster plates, the sandboard, and the front axle. Circle irons, curved straps, guide the rotation and limit how far the axle can swing. Additional straps and stays tie the assembly to the hounds in reach, resisting twist and side thrust. Every one of these connections is a joint. Every joint is a potential failure point. When the bolster plates are secured with hot riveted straps, and those straps develop play over time, the entire fifth wheel assembly begins to shift. The bed and running gear no longer move as a unit. Instead, they surge separately, the bed pushing forward on a downhill grade, the axle dragging behind, then the opposite, on an uphill pull. Each surge translates into a higher peak load on the animals and more shock to the hardware. Brake gear presents a different problem. Wagon brakes use a simple mechanical linkage. A lever on the bed operates a rock shaft which pulls on hangers connected to brake shoes that press against the wheel rims. Every pivot point in this system, rock shaft bearings, hanger pins, shoe connections, is a joint that can develop play. Slack in the linkage means the brake engages suddenly instead of smoothly. The shoes grab, the wheels skid, and the uneven force accelerates wear on both the shoes and the wheel rims. Worse, a brake that grabs unpredictably can cause the wagon to slew sideways, especially on a side hill or in soft ground. Hub bands and tires are the third critical location. Iron tires are shrunk onto wooden wheels while hot. As the tire cools, it contracts, compressing the felloes, the curved wooden segments that form the rim, and holding everything tightly together. Small straps and fasteners keep the tire from creeping around the wheel during use. If those straps loosen, the tire begins to shift. It rocks against the felloes with each rotation. The rocking motion crushes spokes where they enter the hub, loosens the hub band, and eventually causes the tire to roll off entirely. A lost tire is a disabled wagon. In all three locations, fifth wheel, brake gear, hub bands, the standard fastening methods of the period are adequate for light use. But under the sustained vibration and shock of long-distance freighting or emigrant travel, they fail predictably and repeatedly. Cold-set rivets offer a solution. At the fifth wheel perimeter straps, where side thrust tries to elongate bolt holes, a cold-swelled rivet fills the hole and resists movement. At Einbau, brake hangers eliminating play produces smooth, progressive engagement. At hub band straps, tight fasteners prevent the creep that leads to catastrophic tire loss. A wagon may have hundreds of fasteners, but the way a few dozen around the pivots behave can decide whether a train keeps schedule or loses a wheel in the middle of a crossing. Two near-identical wagons stand nose to tail on a compacted lane. A spring scale hooks to each tongue in turn. Helpers lean into the traces while a smith notes the readings on a slate. Most frontier tests are informal. Teamsters say this one pulls easier or that rig fights the animals. The judgment is subjective, based on feel and experience. But with tools already in use for agricultural work, spring scales, steelyards, lever balances, it is possible to measure draft load directly. The test protocol is simple. Load both wagons identically. Ensure tire condition, axle lubrication, and wheel alignment are equivalent. Hitch them on the same hard-packed surface. Use the spring scale to measure the force required to start the wagon moving, and the steady-state force needed to keep it rolling at walking speed. The wagon built with standard hot riveted joints shows predictable behavior. The initial pull to overcome static friction is high. As the wagon begins to move, the load drops slightly, then surges with each bump or irregularity in the ground. The scale needle jumps, 200 pounds, 250, back to 200, up to 270. The wagon rebuilt with cold-set rivets in key joints, fifth wheel straps, brake hangers, hub bands, shows a different pattern. The initial pull is similar, but the surging is reduced. The load remains closer to steady state. The scale needle still moves, but the variations are smaller. The difference might be 10 or 20 pounds of peak force, a small percentage of the total load. But that peak force is what fatigues animals. Oxen pulling steadily at 200 pounds can maintain that effort for hours. Oxen jerked repeatedly to 270 pounds tire faster, overheat, and require more frequent rest. Over the course of a day, reduced surging translates into more consistent pulling, less need to stop and cool off the team, and potentially an extra mile or two within the same work window. Agricultural engineering tables from the period provide context. Draft load for a wagon depends on surface condition, tire width, and total weight. On hard dirt, the pull is roughly 30 to 50 pounds per ton of load. On loose sand or soft ground, it can be 3 to 5 times higher. A loaded emigrant wagon, 3,000 pounds total, requires 90 to 150 pounds of steady pull on firm road, more on grades or rough ground. Freight wagons carrying 3 to 6 tons require proportionally more. A 4-ton load on level, firm road might require 300 pounds of steady pull. Add grades, ruts, and soft patches, and the peak loads can reach 500 pounds or more. Any reduction in peak force, even a few percent, matters. It shifts the work from the edge of the animal's capacity back toward the sustainable middle range. Teams that can pull steadily without repeated overload stay healthier, last longer, and cover more ground per day. The test also reveals something else. Quiet wagons pull more smoothly. The absence of rattle is not just acoustic, it is mechanical. Joints that do not shift, do not convert forward, pull into internal impacts. The energy goes where it should, into overcoming rolling resistance and moving the load. A reduction of a few dozen pounds of peak pull is barely noticeable in a single tug. But multiplied by thousands of starts and stops over 2,000 miles, it can be the difference between 10 miles per day and 12. A freight company ledger lies open on a desk. The columns list departure dates, destinations, wagon numbers, loads in pounds, arrival dates, repair stops, and costs charged. Nowhere does the ledger mention rivets, bolts, or fastening methods, but every entry depends on them. Freight contractors think in dollars and days, not decibels and draft loads. A wagon is valuable if it completes trips on schedule without excessive breakdowns. It is expensive if it spends days sitting on blocks while wheels, axles, or running gear are repaired. The economics are straightforward. A freight contract specifies tonnage, route, and delivery date. The contractor calculates how many wagons are needed, how many animals, how much feed, and how many spare parts. Profit depends on completing the contract with minimal unscheduled costs. Mechanical failures are unscheduled costs. A broken wheel costs time, half a day to a full day for field repairs, longer if the train must return to a depot. It costs materials, a replacement wheel, tire, or hub. And it costs animal condition because the train sits idle while the rest of the schedule compresses. Over a season, a wagon that requires 3 extra repair stops costs the company 3 days of delays, 3 sets of replacement parts, and the opportunity cost of freight that could have been moving. A wagon that requires no extra stops beyond routine maintenance is worth more, not because it is faster, but because it is predictable. The mechanical improvements described in earlier chapters translate directly into ledger effects. Tighter joints mean fewer fatigue cracks at critical points. Fewer cracks mean fewer sudden failures. Fewer failures mean more days spent moving freight rather than waiting for parts. Typical freight distances in the period range from 600 to 700 miles for government supply runs to interior posts, up to 1,000 or more for longer routes. Emigrant parties cover roughly 2,000 miles from the Missouri River to Oregon or California. At 10 miles per day, a 600-mile haul takes 60 days, not counting layovers for weather, rest, or repairs. If breakdowns cost an IOS additional 6 days over the season, the total trip time is 66 days. If improved wagon construction reduces breakdowns to 2 days, the trip takes 62 days. 4 days saved does not sound like much, but across a season with multiple round trips, those days accumulate. A contractor who can complete 3 round trips instead of 2.5 delivers more freight, earns more revenue, and builds a reputation for reliability that wins future contracts. The same logic applies to emigrant parties. Families on the Oregon Trail face a different kind of deadline. The mountain passes close with snow in October. A party that leaves Missouri in May has roughly 5 months to cover 2,000 miles, an average of 13 to 14 miles per day. Most parties manage 15 to 20 miles on good days, especially early in the season when animals are fresh and the trail is dry. But delays accumulate: river crossings, weather, illness, and mechanical breakdowns. A wagon that loses a wheel or breaks a reach can cost a full day or more. Multiply that by several breakdowns over the journey, and the party arrives at the mountains in late September instead of early September. No 19th century ledger lists cold-set rivets as a line item, but they show up indirectly in fewer condemned wagons, in more freight delivered before snow closes the passes, and in the simple notation, "Arrived on schedule." A diary entry, penned in cramped handwriting, notes, "Delayed this day with broken wheel." Another, from a different party, complains of constant stopping to tighten bolts and repair reaching irons. A third, more fortunate, simply records miles made without comment. Emigrant and freighting accounts from the 1840s through 1860s seldom mention rivets, fasteners, or joint design. But they do distinguish between wagons that stood the road and those that constantly failed. The Oregon-California trail system carried hundreds of thousands of emigrants westward over a period of several decades. Most traveled in wagons built hastily in Missouri or Iowa, purchased from local builders, or adapted from farm use. Quality varied widely. Some wagons were well designed and carefully constructed, with seasoned wood, properly fitted hardware, and attention to joint integrity. Others were thrown together quickly, using green timber, oversized holes, and minimal reinforcement. Both kinds faced the same 2,000-mile test. The well-built wagons appear in the historical record, mostly by their absence from complaint. Diaries note daily miles, grass and water locations, weather and occasional accidents, but mechanical issues are rare. The inference is that the wagon performed as expected, requiring only routine maintenance: greasing hubs, tightening a strap, replacing worn brake shoes. The poorly built wagons dominate the breakdown accounts. Wheels collapse, often because spokes have loosened in the hub or the tire has rolled off. Reaches break near bolt holes where repeated stress has split the wood. Fifth wheel assemblies develop so much play that the bed rocks visibly on the running gear, making the wagon difficult to control on side hills or descents. Emigrants respond to these failures in different ways. Some carry spare parts and have enough mechanical skill to make repairs on the trail. Others abandon damaged wagons and transfer cargo to remaining vehicles, overloading them and increasing the risk of further failures. A few turn back or stop at frontier settlements, unable to continue. The common element in most breakdown accounts is vibration-induced wear. Joints that start the journey with small clearances develop larger gaps over time. Hardware that was marginally secure works loose. Wood that was dry and strong splits under shock loads after weeks of battering. The wagons that avoid these failures share certain characteristics, even if contemporary accounts do not name them explicitly. They are built with tighter joints, their fasteners fit closely and do not rattle. Their running gear remains square and true, so wheels track properly and tires stay in place. Cold-set rivets used in strategic locations fit this profile. A wagon built with swelled rivets in the fifth wheel assembly, brake linkage, and hub bands would naturally fall into the held-up well category, even if the diary never mentions the fastening method. The cleanest evidence for a good fastening practice is not praise in the written record. It is the absence of complaints and the simple notation, "Made our miles." A well-built wagon, its joints tight and quiet, sinks axle-deep in spring mud. The teams strain. The wheels do not turn. The wagon does not move. Fastening method can eliminate rattle and reduce internal losses, but it cannot change terrain, compensate for overload, or fix gross design errors. This chapter establishes the limits of what improved joints can accomplish. Draft resistance comes from two sources: internal friction within the wagon and external friction between the wheels and ground. Cold-set rivets address the first. They do nothing for the second. Ground friction depends on soil type, moisture, tire width, and load per inch of tire contact. A narrow tire concentrates weight, sinking deeper into soft ground and requiring more force to roll. A wide tire spreads weight, floats higher, and rolls more easily. Even a perfectly fastened wagon must overcome soil resistance. On hard-packed dirt or grass, this might be 30 to 50 pounds of pull per ton. On loose sand, it can be 3 times higher. In spring mud, after heavy rain or snowmelt, it can reach 5 times the hard ground baseline or more. No amount of joint tightening changes this. A wagon built with cold swelled rivets in every joint will still bog down in the same mud as a wagon with loose bolts. The difference is what happens after the mud firms up. The loose-jointed wagon emerges from the mud with stressed hardware, elongated holes, and new cracks. It may require hours of repair before it can continue. The tight-jointed wagon emerges ready to roll. Its running gear is still square. Its fasteners are still secure. It lost no time to mechanical failure, only to terrain. There are also locations where bolts, pins, and bushings remain necessary. Rotating hubs, for example, require clearance by design. The axle arm passes through the hub on a greased bearing surface. If this joint were tight, the wheel could not turn. Similarly, the king bolt at the fifth wheel must allow rotation for steering. Locking it solid would immobilize the front axle. The art lies in knowing where movement is intended and where it is not. At a hub, clearance is necessary. At a brake hanger pin, it is destructive. Wagon builders and wheelwrights of the period developed this knowledge through experience. Manuals emphasize proper wheel dish, the slight outward angle of the spokes, which distributes load and prevents crushing. They warn against overloading, which stresses every joint and bearing beyond design limits. They recommend wide tires for soft ground and narrow tires for hard surfaces. Understanding both domains, joint design and operating limits, is what separates marginal outfits from durable ones. The silent wagon still bogs in the same mud, but when the trail finally firms up, it rolls again without a single extra hour in the repair column. A line of freight and stage wagons leaves a river town. Some rattle audibly as they cross the cobbles. Others pass with only harness jingle and hoof sound. Frontier transport history often spotlights dramatic stories: the Pony Express, narrow escapes from hostile forces, heroic crossings of mountain passes. What it discusses less often are the mechanical standards that kept everyday freight moving year after year without headlines. By the 1860s and 70s, the overland freight network is extensive. Firms like Russell, Majors, and Waddell operate hundreds of wagons, thousands of animals, and relay stations spaced along major routes. Stage lines run on fixed schedules carrying mail, passengers, and light freight. These operations depend on predictability. A stage must arrive on time, or passengers miss connections. A freight wagon must deliver government supplies to interior posts before winter closes the trails. Reliability matters more than occasional bursts of speed. Wagon builders and repair shops supplying these firms respond to repeated failure modes. They learn which joints fail most often. They experiment with tighter tolerances, better materials, and improved fastening methods. Over time, the trade expectations for good work shift. Cold-swelled rivets are part of this shift, but not the only part. King bolt stays are redesigned to resist nut loosening. Brake hardware is built with closer-fitting pins and bushings. Bolts are specified with larger heads and washers to distribute clamp load. Wheels are built with better dish and tighter spoke fit. The cumulative effect is that wagons become quieter and more reliable. A wagon leaving a shop in 1870 is measurably better than one built in 1850, even if the basic design, bed, running gear, wheels, brakes, is similar. The improvements are incremental, not revolutionary. No single innovation transforms the wagon overnight, but each refinement removes a source of failure, reduces maintenance, and extends service life. Operators notice. Reliable wagons win contracts. Shops that build reliable wagons earn reputations. By the later 19th century, the expectation that freight wagons should run tight and nearly silent is so common it no longer has a name. It is simply how good work is done. The origins of specific techniques fade from memory. A wheelwright in 1880, asked why he drives certain rivets cold instead of hot, might answer because it holds better, without knowing that the practice developed from decades of blacksmiths, fighting bolt loosening and split reaches. What matters is that the knowledge persists, embedded in shop practice. Apprentices learn from masters. Manuals document standard methods. Wagons built to these standards perform measurably better than earlier models. The freight and stage network continues operating into the 1870s and 80s, gradually displaced by railroads. But even as rails take over long-haul freight, local wagon traffic remains essential. Goods must move from rail depots to ranches, mines, and towns. The lessons learned in the long-haul era carry forward. By the time railroads displaced most wagon traffic, the expectation that wagons should run tight and nearly silent was so common it no longer had a name. A modern semi-trailer frame sits in a fabrication shop. Its structure shows rows of rivets and high-strength bolts, all specified to precise torque values to create clamp load and prevent slip under millions of load cycles. Viewers may assume preloaded joints are a purely industrial-age invention, developed by engineers with formal training in mechanics and materials science. In fact, the logic behind them is visible in refined wagon work from the 19th century. The principles are the same across eras. A joint can fail in two ways. The fastener can break, or the parts can slip past each other, wearing the hole and eventually causing structural fatigue. To prevent slip, the joint must be designed so that friction between the clamped surfaces carries most of the load, with the fastener shank serving as backup. This requires three things: clean, flat mating surfaces, a fastener strong enough to produce significant clamp load, and a method of installation that ensures the clamp load is actually achieved. In modern practice, high-strength bolts are tightened to specified torque, stretching the bolt shank slightly and pressing the joint surfaces together. Rivets are driven in similar fashion, with the upset head and tail creating permanent tension along the shank. In 19th century wagon work, the tools and materials are different, but the goal is the same. A cold-swelled rivet in a carefully drilled hole produces clamp load by swelling the shank until it presses outward against the hole walls. The rivet head and upset tail compress the joint surfaces. Friction between those surfaces carries the load. Mechanical engineers today specify riveted and bolted joints for railcars, trailers, and structural steel. They calculate required preload, design hole tolerances, and specify installation procedures, all to prevent the microslip that leads to fatigue. Wagon restorers and historical mechanics apply similar reasoning when preserving surviving vehicles. They drill holes to close tolerances, select ductile fasteners, and drive rivets or tighten bolts to eliminate play. The result is a wagon that runs quietly and holds up under use, just as the original builder intended. The connection between frontier wagon work and modern engineering is indirect but real. The lessons learned under wagons, where vibration and shock were constant, inform broader vehicle design. The same fight against play and rattle that saved oxen on the plains now saves bearings and structures in modern freight. Technical literature on riveted joints emphasizes the importance of preventing slip. It describes how joints that rattle experience accelerated wear and fatigue. It recommends close-fit holes, ductile fasteners, and controlled installation to maximize clamp load. These are the same issues frontier blacksmiths identified in their repair notes. Screws and bolts are always working loose. The difference is that modern engineers have formalized the solution with calculations, specifications, and standards. The underlying physics, however, has not changed. The quietest mile on a modern highway owes something to experiments made under wooden wagons a century and a half ago. The scene returns to the Platte River Road, Nebraska Territory. Mid-season, 1859. Emigrant trains averaging 15 to 20 miles per day. Freight trains holding closer to 10, all sharing the same thin grass and dusty track. Frontier memory tends to elevate bravery and luck. The stories passed down emphasize courage in the face of danger, endurance through hardship, and the occasional stroke of fortune that saved a party from disaster. These elements are real and important, but the historical record shows another deciding factor: how well wood and iron were persuaded to work together. The wagons moving west in the mid-19th century are products of practical craft, built by wheelwrights, blacksmiths, and carriage makers working with available materials and tools. Their designs are based on decades of accumulated knowledge about what works and what fails. Most are built using standard methods: logs squared into axles and bolsters, wheels assembled from hubs, spokes, and felloes, iron tires shrunk on hardware fastened with bolts and hot-set rivets through generous holes. These methods work adequately for local farm use and light hauling. But long-distance overland travel is a different test. 2,000 miles of vibration, shock, dust, wet-dry cycles, temperature extremes, and uneven terrain expose every weakness in the design. Joints that are marginally secure at the start work loose over time. Hardware that fits loosely develops rattle and then fails. The wagons that survive this test without excessive breakdowns are the ones built with tighter joints, better materials, and attention to how hardware behaves under load. Cold-set rivets are one tool in this broader effort, a method that eliminates clearance, creates clamp load, and prevents the microslip that turns into catastrophic failure. The math of survival on the overland trails depends on animal power, distance, and time. Emigrants and freight contractors alike face fixed limits. Oxen or mules can pull only so much. Grass and water are available only in certain locations, and the weather imposes deadlines that cannot be negotiated. Within those limits, small improvements accumulate into meaningful advantages. A wagon that requires fewer repair stops covers more miles per season. A wagon that pulls more smoothly preserves animal condition, allowing the team to work longer before breaking down. A wagon that does not rattle itself apart delivers its cargo intact. Practices like cold swelled rivets do not appear as bold headlines in contemporary accounts. They appear instead as slightly higher daily averages. Fewer breakdowns noted in trail diaries, teams still fit enough to haul another season, and ledger entries that record arrived on schedule instead of condemned at Fort Laramie. When a wagon rolled out of a competent shop and stayed tight and nearly silent for a full season, its success showed up nowhere on the vehicle itself. It was recorded instead in a freight ledger's small figures, fewer repairs, steady miles, and the same teams counted again in the spring.